Yes, welcome to DC Economics. So I'm going to take you through the concept about the HESSIAN matrix. HESSIAN matrix is a powerful tool in optimization and can help to determine the nature of the critical points, maximum or minimum or saddle points for the function of multiple variables. So actual HESSIAN matrix is an extension of HESSIAN matrix, which is the matrix of the second partial derivative of the scalar valued function of several variables. So actual HESSIAN matrix involves the tools that are applied in optimizations. And the HESSIAN matrix incorporates both the second partial derivative of the objective function and the first partial derivative of the constraint function. In economics, HESSIAN matrix is commonly used in the study of microeconomic theory, particularly in the context of utility maximization subject to the budget constraints. So in utility maximization, where we tend to look on how individuals or consumer acquire a great satisfaction after consuming a certain good or services. So if you want to check out the maximum or the minimum of that satisfaction, we can apply the HESSIAN matrix. So in economics, HESSIAN matrix is actually applied in the study of a particular context in optimization theories. So by examining the eigenvalues of the HESSIAN matrix, that are critical points, economists can determine whether the solution corresponds to the maximum or minimum or saddle points. So the HESSIAN matrix plays a crucial role in understanding the local properties of the constraint. A HESSIAN matrix is given in the format of the function of xy, which is equal to the objective function, given g bracket xy, given the given budget constraint. So the functions of the given xy and lambda is equal to the function of xy is equal to the function of the bracket xy bracket plus lambda times the budget line or the budget constraint. So we develop the budget constraint and we plug into this formula over here. Is where now this is a step forward for understanding or constraining the HESSIAN matrix formula. So we take the function of x times given x and y and lambda, which we equate is equal to 0. We apply the first order derivative from the given function. We apply also the function of y times xy lambda is equal to 0, and the function of y xy lambda is equal to 0. So we actually take the first order condition from the given function, whereby we consider to take out the partial derivative of the function in respect of the given variables, that is x, y, and lambda. Then after that is actually we apply the second order conditions where we develop the HESSIAN matrix determinant. So the HESSIAN matrix is actually very concerning in this step. So we apply the HESSIAN matrix now to see if the function is minimum or maximum. So the given HESSIAN matrix is given by taking the h, that is the absolute of h bar, which is equal to the function of xx, function of yx, function of xy, function of yy, gx, gy, 0, gx, and gy. Remember, the gx and gy determine the given lambdas on the given budget constraint of the equation. So actually the function of x on the given xy, which is equal to 0, and the function of y given xy lambda is equal to 0. Function of lambda xy lambda and y. So when you take function of x times x, is where we obtain our function of xx to the given objective, to the given HESSIAN solution. So we take function of x times y, we get function of xy, and we take function of y times lambda, that give you the function of x lambda, that is gx. Again, we take function of x times x, that give you function of yx. We take function of y times x, function that is give you function of yx, function of yy, gy. And take the function of lambda gx, that is a gx, a gy, which is equal to 0. So we develop the given HESSIAN matrix in respect to the given partial derivative that we've obtained from the formula from the construction budget line. So the given body Hessian matrix, that is determinant, if you obtain it is less than 0, this proves that the function is minimum. And if the body Hessian matrix determinants, that is less than 0, give you maximum, that is the maximum function. If the determinant is less than 0, this means that the function is maximum. Now it will be better now we go through an example. Let's look at the following example for better understanding of the concept about the body Hessian matrix. Now you are asked to optimize the given function z is equal to 4x squared minus 2xy plus 6y squared, subject to the given constraint, that is x plus y, which is equal to 72, and hence now find the critical points. Now from the Lagrangian, that is x y lambda, which is equal to the function of x y plus lambda, then under given a budget constraint, is where we take now lambda bracket xy lambda bracket, which is equal to, now we take the given function of xy, that is z, that is 4x squared minus 2xy plus 6y squared plus lambda times given budget constraint. So the budget constraint actual is constructed by taking 72 and take x to the right hand side and y to the right hand side. So this means that it will be equals to 72 minus x minus y. Now given lambda, given Lagrangian, that is xy lambda, which is equal to 4x squared minus 2xy plus 6y squared, we take out 72 times lambda, lambda times x, that is x lambda, minus y times lambda, that give you y lambda. So we apply the first order condition by taking the partial derivative of the given Lagrangian in respect of each variable, that is x, y, and lambda. So when we take out the partial derivative of dl in respect of dx, that will give you 8x minus, we take the partial derivative in respect of x, that will give you 2y minus, again, which is equal to 0. That is equation number 1. We take dl over dy in respect of y. Now it will be 2x, then plus it will be equals to 12y, that is 2 times 6, then 2 minus 1, that is 12y minus lambda, which is equal to 0. That is equation number 2. We take out also again dl in respect of d lambda, that will give you 72 minus x minus y, which is equal to 0. That is equation number 3. Now after doing so, now let's find the critical points. So let's solve and obtain the critical value, that is x, y, and lambda. So we take the first order derivative, that is 8x minus 2y minus lambda. We take out 2x, we make the subject to the 7 2x, that is 72 minus x minus y. So it will give you, now we take out 72 minus x minus y, which is equal to 0. Now after taking out the 72 minus x minus y, which is equal to 0, we make x the subject. So it will give you negative x, which is equal to, we take out 72 to the right hand side, that is 0 minus 72, then plus y. This will give you now negative x, which is equal to 72 plus y. Let's divide by negative both sides. So divide by negative. This will give you x, which is equal to positive 72 minus y. So that's the equation number 4. Now let's consider now the second order conditions of the given function, and we plug in the values of x to the first and the second derivative equations. So we take out 8x minus 2y minus lambda, which is equal to 0. Let you plug in the values of x inside. So it will be 8 times 72 minus y minus 2y. So minus 2y minus lambda is equal to 0. So this will give you now 8 times 72, that will give you 576 minus 8y minus 2y minus lambda, which is equal to 0. So it will be 576 minus, we take out negative 8y minus 2y, that is negative 10y minus y, which is equal to 0. Now after taking that, let you plug in the values of x to the second equation, that is 72 that is negative 2x plus 12y minus lambda, which is equal to 0. We plug in the values of x, that is 2 times 72 minus y plus 12y minus lambda is equal to 0. Take negative 2 times 72, that will give you negative 144 plus negative 2 times y, that is 2y, plus 12y minus lambda, which is equal to 0. It will be negative 144 plus 2y plus 12y, that is 14y, minus lambda, which is equal to 0. That is equation number 6. So after doing so, now let's rearrange these new equations that we have developed, and rearrange out the new equations. That is equation number 4, number 5, and number 6. So this will be as follows. So the equation number 5, that is given by taking 4, we take the equation number 4 and 5 and 6, that will be equals to x, that is 72 minus y, that's equation number 4. Then equation number 5 is 576 minus 8y minus 10y minus lambda, that is equal to 0. We take out again the 6th equation, that is 144, negative 144 plus 14y minus lambda, which is equal to 0. That's equation number 6. Now choose either of the equation number 4, number 5, or number 6, and make out the subject, the given lambda. So when we take out the equation number 6, that is negative 144 plus 14y minus lambda, let you make lambda the subject. It will give you now negative lambda. It will be equals to negative 144 plus 14y minus y is equal to 0. That will make lambda the subject. It will be negative lambda, that is 0. Then 0 plus 144, then minus 14y. So it will be negative lambda is equal to 144 minus 14y. Divide by lambda both sides, the negative both sides of the equation. It will be lambda is equal to negative 144 plus 14y. So that will be equation number 7. Also, we consider now to take out lambda and plug into the 5th equations, that is 576 minus 10y minus lambda. So under given lambda, that is negative 44, 144 plus 14y, we take out this equation to the 5th equations. So when we plug into this equation, this means that this will be 576 minus 10y minus lambda is equal to 0. So when we plug in the given lambda equation, it will be 576. Then minus, we take out 10y, negative 144 plus 14y. So it will be 576 minus 10y plus 144 plus 14y. Now, can you plus now the like terms? That is 576 and 144. It will give you 720. Then it will be negative, then plus 144y. So it will be, we take out 10y, then plus 14y is equal to 0. So this means that will be 720. Then here it will be equals to negative 10y plus 14y. That will give you 24y, which is equal to 0. Now let you make y the subject and solve for y. So it will be now negative 24y, which is equal to 0 minus 720. So we divide by negative 4 both sides. Now the values of y will be equal to 720 divided by negative 4. That will give you exactly negative 180. So after obtaining the values of y, that is negative negative 180. Now from the given equation, now we take out the value of y and we plug into the values of x. So from the given equation of x, which is equal to negative 44, negative 144 plus 14y, we plug in the values of y, that is negative 180. So when we take it the equation of x, which is equal to 72 minus y, we plug in the values of y, that is negative 180. So actually the values of x would be equals to 72 minus, that is positive 180. That will give you 252. Now after obtaining the values of x, now let's solve the value of lambda. Let you take the values of x to the 6 equations so as you can obtain the value of lambda, the critical point lambda. So since we have solved the values of x and the values of y, those are the what are known as the critical point. So we need to go straight forward and look on how we can solve the lambda value, the critical point value of lambda. So this means that when we take out 14y minus y, which is equal to 144, as I told you earlier, the value of lambda will be equals to now, when you plug in the value of lambda inside the equations, they mean that the value of lambda will be equals to negative 44 plus 14 times negative 118. So this will give you 144 minus 19 minus negative 180. So the value of lambda will be equals to 2664. So after obtaining the value of lambda, now it is possible now, since the value of lambda is 2664, now let's prove out our critical points to the equation before finding the body Hessian matrix. So x, which is equal to 72 minus y, and 576 minus 10y minus lambda is equal to 0, and 14y minus lambda, which is equal to 144. Now let you plug in the values of x and y to see the results. So when you take out x, which is equal to 72 minus the given value of y, that is negative 80, it is true and it is fact that the answer will be equals to 252. So the given budget constraint is where now we take out the values of x, negative 180, plus the given value of x, that is 252. The result will be equals to, the answer will be equals to the given budget constraint. So when we plug in again to the second equation, also to the said equation, that is 14 times 80, negative 180 minus 2664, the answer will be equals to 0, as we have did to our previous equations. So when you prove out this critical point to the given partial derivative, when you take 72 then times given 252 minus negative 180, the answer will be equals to 0. And when you cross check it to the budget constraint, the answer would be the same. So for that case now, when you try to prove these critical points, you obtain the same results as the partial derivative indicates. So when you plug in to the second order derivative of dl over dy, that is 2x plus 12y minus lambda is equal to 0, you will see the result will be equals to 0. And when we take the dl over dx on the given function of 8x minus 2y minus y is equal to 0, when we plug in 8 times 252 minus negative 2 times 180, then minus negative 264, the answer also will be equals to 0. Also, when you take to the given badge constant, that is x plus y, which is equal to 72, when you plug in the values of x, that is 252, and the values of y, that is negative 180, the answer will be equal to 72. And so let's now apply the second condition under body Hessian matrix. So this is the last step to prove if the function is maximum or minimum under the given optimization principles. So the second condition of body Hessian matrix is given by the function of xx, the function of xy, gx, and the function of yx, function of yy, gy, gx, gy, 0. So actually develop this body Hessian matrix format by consider the partial derivative of dl in respect of dx, the dl in respect of dy, and dl in respect of d lambda. So in respectively to what we have obtained previous on the partial derivative, this means that from our partial derivative, that is dz over dx, that is equal to 8x minus 2y minus lambda is equal to 0. dz over dy, that is negative 2x plus 12y minus lambda is equal to 0. And dz over d lambda, that is 72 minus x minus y, which is equal to 0. So under the format of this body Hessian matrix, we consider to take a function of xx, that is 8, and negative 2. We consider the place where there is values, there is a rate of x. So this means that it will be 8, negative 2. And since 72 has got no x, we consider the values that is as a coefficient of x, that is negative 1. We take with function of xy, that is 2, 12, together with negative 1. We consider also the given lambda equation, that is gx and gy, that is negative 1 and negative 1, which is equal also to 0. So we find the determinant from this given function. That will give you, we hide the left and we take out the value. That will be equal to 8 times given elements 12, negative 1, 0, minus negative 2. We hide also the center values, that will be equal to negative 2, negative 1, 0, minus negative 1. We hide on the right hand side, and the above, that will remain with negative 2, 12, negative 1, and 1. That will be equal to 8 times negative 1 plus 2 times negative 1 minus 1 times 2 plus 1. So the result now would be equals to negative 8 minus 2 minus 14. That will be equals to negative 24. So the body Hessian matrix determinants give up the results, that is negative 24. And since negative 24 is greater than 0, under the condition of body Hessian matrix, if the determinant of the body Hessian is greater than 0, actually this proves that the function is maximum. And if the determinant under given body Hessian matrix is less than 0, prove that it is minimum. So under critical point now, the function is maximum at a given value of x, that is equal to negative 108, y is equal to 180, and lambda, that is equal to 2664. That's mark the end. Welcome to DC Economics. Don't forget to watch other videos. Bye bye.